First speaker this morning is Stuart Raby, and he will talk about SU6 orbifold gut and on M4 times RP2 gauge Higgs unification.
Okay, the title's pretty clear, but it will become more apparent as we go on. This is based on a paper I wrote recently with my student Archana. And it's also based on previous work in the literature discussing what's called non-local gut breaking. And so I'll say a few words about non-local gut breaking, but these are the papers that were motivating the work that we did. So in string models, this is not a string theory talk, but in string theories, particular the heterotic string, you can look for orbifold type guts in certain limits of the heterotic string. For example, if you compactify the heterotic string, the E8 cross E8 heterotic string on a 6-dimensional manifold, and if you let two of those, which is a product of three 2-dimensional tori, if you let two of those tori be large and the other 4 dimensions be small, 2 dimensions be large and the other 4 dimensions small, you might have something which looks like a gut, and in particular in the E8 cross E8 mini landscape models that we constructed, we always had an SU6 orbifold gut in that limit. And then you might want to understand if you have an SU6 orbifold gut, which is then further orbifolded down to a 4-dimensional theory, which has the standard model, you want to understand if gauge coupling unification works in such theories. You start out with SU6, which contains SU5. You orbifold down to the 4-dimensional standard model, and you then check gauge coupling unification, and you have to calculate the threshold corrections coming at the gut scale, or from the KK modes that come above the compactification scale, and ask whether gauge coupling unification works. We did this, and we can get it to work. It's an accommodation of such in the mini landscape models. On the other hand, there's another set of symmetry breaking with Wilson lines, which in which gives you different results in general. And let me describe what kind of differences that you might get. When you do local breaking, even with a Wilson line on an orbifold, which does not have a non-trivial fundamental group, pi1, of the orbifold, then when you smooth out the fixed points on this orbifold, your Wilson lines actually, even though you do Wilson line breaking of the gut symmetry, your Wilson lines will shrink. There's no pi1, so the Wilson lines will shrink to a point, and then what you have is flux breaking at singularities on the orbifold. And that's fine, but that's not. And as a result of that, what you have is gauge group is broken, and it's broken predominantly at the fixed points. The Wilson lines, in this case, can be shrunk to a point where you have non-vanishing gauge flux localized, and that's what's breaking the gauge symmetry when you have local gut breaking. In other words, no fundamental group, so therefore no Wilson line, which can non-trivially wrap a cycle which can't be shrunk to a point. In the case of non-local gut breaking, the manifold has a non-contractible cycle or cycles, and then Wilson lines can break the gauge symmetry at the scale of the cycle associated with the dimension, the length scale of that cycle. And so you might want to have the cycle be of order the gut scale, the 4D gut scale, and naturally break the symmetry at that gut scale. To say this once more, in local gut breaking, the gut is broken at the cutoff scale, not at the scale of the cycle that you're wrapping. And you have standard model at some fixed points, typically. So there's fixed points where you have the standard model, and there are fixed points where you may have some gut, but you can put your matter at the standard model fixed points, and you can put your matter in the bulk, but you've explicitly broken by this local symmetry breaking, you've explicitly broken the symmetry, the gut symmetry at certain fixed points. When you have non-local symmetry breaking, the gut is spontaneously broken by the Wilson line at the compactification scale, the symmetry is spontaneously broken at all points, even at the fixed points. So even when you smooth it out, you've spontaneously broken the symmetry, but the symmetry is only spontaneously broken everywhere. And above the scale of symmetry breaking, you have a gut. And so it's more like the standard 4D guts, where you have some Higgs sector which spontaneously breaks the gauge symmetry. Above that scale, you might have the gut symmetry. And so you might minimize the threshold corrections coming from gauge coupling unification in such non-local symmetry breaking scenarios. And so what we wanted to do is to try to construct an SU6 orbifold gut in 6 dimensions. The 6 dimensions was on the Minkowski space across the torus, and then the torus is modded to give you a manifold, a 2-dimensional manifold with a non-trivial pi1, which in this case is Z2. So you can actually wrap the Wilson line around this orbifold. It may have fixed points, but even if you smooth out these fixed points, the Wilson line won't be shrunk to a point. So that would be non-local gut breaking. The orbifold that we've constructed is given in this paper, the first paper by Hebeker. We have an n equal to 2 symmetry in 6 dimensions, which actually effectively looks like an n equal to 4 symmetry in 4 dimensions. And in fact, we had to have this because otherwise we couldn't construct, we didn't have enough symmetry to construct the orbifold with an n equal to 1 supersymmetry in the end. So I'll discuss gut and SUSY breaking. There are 2 possible choices. Gauge coupling unification we'll calculate and then discuss some conclusions. So here's our SU6 n equal to 2 SUSY in 6 dimensions. We're writing it in terms of n equal to 1 4D superfields using the analysis which is in Arcani, Hamed, Gregoire, and Wacker paper, and then following more the specific form of the Lagrangian or the action written in this paper by Hall, Nomura, and Smith, who did local gut breaking. So we can actually compare our local gut breaking of the SU6 to a global or non-local gut breaking. The fields are associated with this a vector gauge superfield. All the fields are in the adjoint representation of the gauge group. We can put matter in later in complete multiplets, and I'll show you how you might want to do that later. But what we have so far is just an effective n equal to 4 supersymmetry in 4D with 3 adjoint chiral multiplets and 1 vector multiplet. And this is the Lagrangian, which is supersymmetric within the n equal to 2 supersymmetry. Now this Lagrangian has certain discrete symmetries, parity operations, which we'll mod out by to generate our RP2 real projective space orbifold. So here's the orbifolding. We do 2 Z2s. One is x5 and x6 both go to minus x5 and minus x6. That's a holomorphic projection or involution on the theory, which takes the torus defined in terms of the 2-dimensional surface modded out by translations by 2 pi r5 in this direction and 2 pi r6 in that direction. That defines the torus. So all our fields are periodic functions in x5 and x6. When we do the first orbifolding, instead of a torus, what we get is something which has the topology of a P1 or a surface, a sphere. And what you see here is a pillow. This is the outer surface, there's a back surface, and the whole thing looks like a pillow with 4 fixed points. And so if you actually smooth out those fixed points, you would get something which is a smooth sphere, 2-dimensional sphere. The second Z2 orbifolding is non-holomorphic. It changes x5 goes to minus x5 plus a shift by half the lattice spacing, and x6 goes x6 plus the same shift. And what that does is it takes this torus and it identifies these fixed points with these fixed points and twists around the center. And so what you've taken is this half of the torus and you've identified it with that half with this twist, and that gives you this surface here. Well, this surface here, which is just the a crosshatch over here, and so this surface has a non-trivial Z2. If you smooth this out, if you smooth out these 2 fixed points, you can construct this in a very smooth way by taking a 2-dimensional sphere and identifying antipodal points on a 2-dimensional sphere, and what you get is a disk with the edge of the disk is identified, and that's this part here. This part here is sort of like the edge of the disk, which is being identified. And this manifold has a non-trivial fundamental group, which is Z2. And we can wrap Wilson lines either in this direction or in this direction by going halfway around the sphere. And since it's identified, this point is identified with this point, that's a closed circle, but non-contractible to a point. So that's the manifold, and now what we have to do is tell you how we do gut breaking on this manifold. In order to get all of this symmetry, we had to start with n equal to 2 in 6 dimensions. If we tried to do it with n equal to 1 in 6 dimensions, and you just can't, there's not enough symmetry of the theory. And so you can't mod out by something which is not a symmetry of the theory. So here's how we do gauge and SUSY breaking. In the first case I call choice 1, we have a parity operation here, which is in the space of SU6, which breaks SU6 down to an SU5 cross U1. It acts as this is the diagonal of a 6 by 6 matrix, and it acts in terms of the fields in this way. So when you go around, when you do this parity operation, in this case, you get a breaking of SU6 to SU5. At those 4 fixed points, you don't only have an SU5 symmetry. You don't have an SU6 symmetry at the fixed points. So this would be local breaking of SU6 down to SU5. Here, at the second Z prime, we haven't done anything yet, but we're going to put a Wilson line to break SU5 down to SU3 cross SU2 cross U1. So I'll show you explicitly how we do the Wilson line in a minute to break the SU5 down further. The other choice is with the first Z operation, we don't do any breaking of the gauge symmetry. And we break the gauge symmetry in this case, where you have the shifts. And so it's a non-local breaking of the SU6 down to SU5 cross U1. And so we have 2 possibilities, either breaking SU6 down to SU5 cross U1 locally at the fixed points, or non-locally in the second step when we have the shift symmetry acting as well. And you can actually show that this is really non-local because these parity operations are equivalent to putting a Wilson line into the theory and then gauging away that Wilson line, and in fact put the Wilson line in the 6th direction, gauging it away and generating this holonomy at the endpoints. Anyway, we'll do that explicitly for the case of SU5 breaking. So let's go again, local versus non-local breaking. The first parity operation has 4 fixed points. In both cases, the local gauge symmetry in the bulk is SU6, which is spontaneously broken to SU6 to SU5 cross U1. However, the local symmetry of the fixed points in choice 1 is just SU5 cross U1. In choice 2, the local symmetry at the fixed points is SU6. You've only broken the symmetry by the Wilson line, which is non-local, and it's spontaneous even at the fixed points. Okay, let's discuss the generation of the KK modes. We have to discuss the Kaluza-Klein structure of this theory. All the fields, this is generic fields, all the fields are adjoints in this case. All the fields are periodic in X5 or X6. So we start out with periodic functions X5 or X6, and then the parity eigenstates, either parity under the first Z, you can have plus minus parity eigenfunctions, or parity under the second Z, that's with the hatted index. And so we define these functions, which are now, you start out with periodic functions, and then define the functions which are eigenstates with certain periods, eigenvalues, and these are the eigenfunctions. Written in terms of the general modes, M and N, of these periodic modes, where M goes from minus infinity to plus infinity, and N is an integer which goes from minus infinity to plus infinity. The way, writing it this way is very nice because if you can see which modes exist and which modes are 0. Because, for example, if you take n equal to 0, then you have minus phi of minus m and 0, plus, for example, plus or minus phi of plus m and 0. And here you have phi of m and 0 plus or minus phi of minus m and 0. So the same thing is on both sides. And so in one case, when you have the plus parity here, you only get the even modes for m, okay, so that they add, otherwise they would subtract and you get 0. And for the case where you have the minus parity here, you only get the odd modes for M. And so you can work out which modes exist and which modes don't exist, and therefore include them in the KK structure. So by doing this and analyzing it in this way, you can figure out what the spectrum of KK modes are in terms of M and N plane, where M and N go from minus infinity to plus infinity in this way of doing it. And so in this case, the plus modes, you have even modes for N equal to 0 and M not equal to 0. And for the plus minus case, for N equal to 0, you get the odd modes. And you can work out the rest of the cases as well. But for M and N both not equal to 0, you get all the modes. Okay, and that means that when you get all the modes, you have an effective N equal to 2 supersymmetry or N equal to 4 supersymmetry when you calculate the beta function contributions of all of these modes. And that sums up to 0. Okay, so choice 1, the degrees of freedom after the first orbifolding is given by this. We broke down the SU6 to SU5, so this is the SU5 subspace of the vector modes. These are plus modes, so we get 0 modes there. And out of the chiral adjoint, we get 0 modes here and here. And this is where our Higgses are going to come from. So our 5 and 5 bar of SU5 are coming out of the chiral adjoint, and when we do the breaking of SU5 down to the standard model, we'll just retain the Higgs doublets and get rid of the color triplets. Okay? And the same thing occurs here, except here we didn't break the symmetry at the first step, we only broke the symmetry at the second step. And as a result, we get the Higgses are coming out of a different chiral adjoint in this case. Okay, so that's just a simple difference between choice 1 and choice 2. Let's discuss the SU5 breaking now via a Wilson line. So a Wilson line means that your gauge field, A5 gauge field, which is sitting in V, think of it in the Wess-Zumino gauge. So you have the standard gauge freedom in the Wess-Zumino gauge, you have the A5 gauge field, and we'll take that one to have a non-zero vacuum expectation value in this direction, which in fact would break SU6 down to SU3 cross SU3. Of course, when you combine it with breaking SU6 down to SU5 cross U1, the end result will be SU3 cross SU2 cross U1 squared. So this is our SU5 subspace, and you see that we'll break it down to SU3 cross SU2, and there's a U1 coming out of there, which would be hypercharge. So SU5 is, this Wilson line will break SU5 down to the standard model. I should say something about this Wilson line. Remember, it's a constant background gauge field. So the question is, how can you have a constant background gauge field when under the parities, in particular, say this parity, the derivative in the 5 direction, x5 goes to minus x5. So the derivative goes to minus the derivative, and the only symmetry is where a5 goes to minus a5. But that's not a constant. Well, it is, in fact, because we'll define a generalized parity operation now where the parity is a combination of this parity times a gauge transformation. So under a discrete gauge transformation, in fact, by this amount, A5 prime, where A5 first used this parity operation, A5 went to minus A5, and now you apply a gauge transformation, and A5 prime is equal to A5, is a constant. And so the new parity operation is a generalized parity operation, which is parity times a gauge transformation, which is still a symmetry of the theory. Okay, this parity operation, in fact, is a gauge symmetry which is periodic, so you're allowed to use this periodic gauge transformation. Actually, under a periodic transformation, it goes to minus itself, but that's an element of the center of the group, and it doesn't do anything to the adjoint gauge fields. Okay, so SU5 breaking by a Wilson line. Well, typically, you don't put in this non-zero vacuum expectation value to the gauge field and then calculate the mass eigenstates of the theory by looking at the covariant derivative operator and calculating the mass eigenstates that way. Typically, what you do is you do these parity operations. Well, the parity operations are very equivalent to what I'm doing here. We just now choose a gauge where the background gauge field is 0. We make a gauge transformation. You can make a gauge transformation, redefine the A5 vacuum expectation value such that it's 0, and this is the unitary transformation that you have to use to go to A5 equal to 0 gauge. Of course, nothing changes as far as the eigenstates of the theory are concerned because they're all gauge invariant. So this is the gauge transformation, how it acts on the fields. And in particular, if I figure out what are the eigenvalues of the fields under the transformation T, I call those eigenvalues I rho, then a general gauge transformation phi prime goes to a new gauge. These new fields in this new gauge are given by this factor times the original fields themselves. Notice that these fields were periodic under x5 goes x5 plus 2 pi r5, or x6 goes x6 plus 2 pi r6, but the periodicity is not necessarily true anymore in the gauge transformed sector. And in fact, what you get is that these new fields, these gauge transformed fields, when A5 is equal to 0, are no longer periodic if I rho is an even integer, or 2, in fact. And so what are the eigenvalues of the adjoint fields? Well, this is a way of writing the adjoint fields in a simple basis. This is the 3 by 3 basis. We'll call that the color octet of SU3. This is the SU2 triplet of the W's sit here. The Higgses, like I say, there's a color triplet Higgs, and Higgs doublet H up would be sitting here. The T and H down T bar and H down would be sitting here, and there's some singlets sitting along the diagonal. And so what we need to know is what are the eigenvalues of these fields, or these fields under this gauge transformation given by this amount T. And so what you do is you just calculate the commutator of T with these fields, and you find out that anything that is either in this box, which is this 3 by 3 box, or anything in this 3 by 3 box is invariant under the gauge transformation, so that its eigenvalue I rho is equal to 0. But the states in the off diagonal up here, which are the color triplet states, and the x and x bar states, which sit in SU5 but not in the standard model up here, all of these states have eigenvalue plus or minus 2. And as a result, these x and t states are massive. And so we've gotten rid of these vector-like exotics that we don't really want in our low-energy theory. So these are the mass eigenstates. These are the KK masses. They're the masses for any arbitrary m and n is given by m plus I rho over 4. So this is a half for any plus or minus a half for I rho equals 2 or minus 2. And so you see you've shifted the mass of these states. Before I calculate the threshold corrections to gauge coupling unification, let me first say something about what you do with quarks and leptons and Yukawa couplings. Well, in choice 1, your quarks and leptons would have to sit at the SU5 fixed points in 10s and 5 bars of SU5. This is a typical way that people do Yukawa couplings when you have local gauge breaking, and Yukawa couplings are localized at those fixed points. In choice 2, the quarks and leptons sit at the fixed points as well, but they have to be in the complete SU6 multiplets. So you have to put one family of quarks and leptons in a 15 plus 2 6 bars of SU6 at those fixed points. And the Yukawa couplings are SU6 invariant. They're localized at those fixed points. That's where you couple the adjoint Higgses to them. And then what you're going to have to do is you're going to have to explicitly break the SU6 down to SU5 without extra U1s by having a term in the superpotential again at those fixed points, which gives a VEV to a 6 and 6 bar field at some scale. Anyway, that's a detail. Gut scale threshold corrections using the formalism of Galencia, who wrote a very nice simple way of calculating these, which would be an equivalent way of calculating the threshold corrections here as you would do in a string theory. And so you can very easily match this onto string scale regularization. And so what we do is we define the gauge coupling at some scale mu below the compactification scale is equal to the gauge coupling at the cutoff scale, which in the string theory would be the string scale, plus the corrections, the radiative corrections due to all the Kaluza-Klein modes. We know all of these masses. We know all of these beta function coefficients, so all of this can be calculated. This is an infrared, for the massless states, this is an infrared cutoff, which then you get rid of at the end. So what we have in our orbifold gut is we can calculate the threshold corrections at any scale Q below the compactification scale using this formula in terms of 4 parameters, which are M5, M6, the effective mass scale in the 5 direction, the KK mass scale in the 6 direction, the scale lambda, which is a cutoff scale, and alpha at lambda. And what's written down here is what you have in a 4D gut. In a 4D gut, near the gut scale, after doing threshold corrections to the weak scale and 2-loop RG running from the weak scale up to the gut scale, you have what you define as the gut scale where alpha 1 and alpha 2 meet. You see there's a correction here to alpha 3, which has to be typically slightly smaller than alpha 1 and alpha 2 at the gut scale. At any rate, this is an equation which actually approximates what you have from once you run up to the gut scale or near the gut scale, the 4D gut scale, from low energies. This is what an experimentalist would call the gut scale, or what Soft Susie calls the gut scale. And Soft Susie would actually have an epsilon 3 in the calculation as implicit because it never outputs this directly. But anyway, there's 3 parameters here, alpha gut, M gut, and epsilon 3. And so what we're going to do is we're going to just take the difference of these 3 terms for alpha 1, alpha 2, and alpha 3. We get 3 equations and 4 unknowns. These are the 4 unknowns, and these are the 3 knowns. We know what alpha gut is, M gut, and epsilon 3 from low energy physics. You just run up low energy physics up to the gut scale. Of course, the value of epsilon 3 you need at the gut scale depends on the threshold corrections and the Susie spectrum at the weak scale to some extent. So we, in fact, can solve these 3 equations analytically, and we get the M5 and M6 are related to each other by an integer M. M is an integer, which is just gives you the ratio of M6, M5 squared. And well, actually, it's not an integer. M is a function of epsilon 3. So M is a simple function of epsilon 3, and here what I've plotted is choice 1, M is a function of epsilon 3, and for choice 2, this is M as a function of epsilon 3. So quite naturally, in choice 1, you can get positive corrections to epsilon 3, which means that alpha 3 is slightly bigger than alpha 1 and alpha 2 at the gut scale. And for choice 2, typically you get negative threshold corrections when M is getting very small, which means that M5 is much bigger than M6. Okay, so this is a relationship between M5 and M6 in terms of the low energy value epsilon 3 that you would get. This is how alpha inverse of lambda depends on lambda. Lambda is typically of order what you might have thought was a string scale. So let me quickly go, because I don't think I have more than 5 minutes. I got 1. So choice 1, SU6 breaks down SU4 cross U1 locally, but at the scale M5, SU5 is breaking down to SU3 cross SU2 cross U1 non-locally. And so you have the gut above that scale. And choice 2 for M5 is both of these are non-local. M5 is much greater than M6, then M5 first breaks SU6 down to SU3 cross U1. This is not hypercharge. And then at the scale, the lower scale M6, you break down to the standard model, but hypercharge actually renormalizes because it's coming out of 2 different U1s. So it renormalizes all the way up to this scale here, and you get those threshold corrections that I showed you on the previous transparency. In the other opposite limit, M6 much greater than M5, you first break SU6 down to SU5 cross U1, and then M5 breaks it down to the standard model. And you might think that SU6 breaks SU5 cross U1 at that scale, but that's not what happens. Because the Wilsonine that's going in the 6th direction, since we're interchanging, that second Z2 interchanges states or far apart in the X5 direction, even when you go in the X6 direction, you're sensitive to the scale, the lowest energy scale. And so what happens is everything breaks down to the standard model at the low energy scale. And so just as some different examples or benchmark points, if you want epsilon 3 to be 1.5% in choice 1, then look, the M5 and M6 are of order the 4D gut scale. The cutoff scale is around 6 times 10 to the 17 GeV, and everything's perturbative at that cutoff scale. In choice 2, if you needed a negative 2% or 3%, then the compactification scales like the 4D gut scale and the cutoff scale is an order of magnitude higher. So the smallest compactification scale is naturally of order the 4D gut scale, and proton decay as a result in coming from dimension 6 operators is perfectly okay because it's okay for 4D gut scale. Let's quickly compare to local SU6 breaking. In the paper by Hall and Nomura, they also had SU6 in 6 dimensions, spontaneously broken with local breaking. Either SU5 or the standard model, you have either SU5 or the standard model of the fixed points or fixed lines, in fact. You have unification at the cutoff scale, and the compactification scale is a cutoff scale divided by 4, so it's very near the cutoff scale. You have a linear running of the couplings due to fixed lines. We don't have any linear running of the coupling, only logarithmic running of the coupling, and no quadratic running due to the n equal to 2 and 6D. This is true in both cases, what I presented here in their paper. We were motivated by solving the string unification problem. Note that the cutoff scale of the order is of order the string scale, gauge coupling unify at the compactification scale. Question, is there a heterotic orbifold which has the same effective 6D limit? Well, in this paper by Hebricker and Tripletti, they wrote down a product of 3 tori and a Z2 cross Z2 orbifold, which doesn't look anything like what we did in the effective 6D theory, but if you take the x1 and x2 directions to be large directions and the other 4 directions to be small directions, they showed in that paper that this looks like RP2. So you have an effective orbifold gut which looks like RP2. Of course, they didn't do a heterotic string. They just wrote down an orbifold. You can show that this orbifold in the language of Donaghy and Wendland, who classified all these Z2 orbifolds of T2 cross T2 cross T2, is equivalent to what they called the 0-3 classification. And well, in the paper by these authors, Blaszek et al., they found the MSSM model on orbifolds very similar to one constructed in our orbifold gut. They found very nice models with 3 families of quarks and leptons, etc. But it wasn't the model that we actually looked at here in our 6D orbifold gut. And it's not the Hebricker-Tripletti model either. And in fact, I asked Patrick to look at the Hebricker-Tripletti orbifold and ask what kind of theory that you can get as an orbifold string theory. And the result is the Hebricker-Tripletti orbifold does not lead to chiral matter. So there's only vector-like matter in that theory. And so that's a problem. So we have verified that non-local gut breaking can give gauge coupling unification at a compactification scale, which is the 4D gut scale, and it's consistent with low energy data. And the cutoff scale is of order a few times 10 to the 17 GeV, naturally of order a typical string scale. However, it would be nice to find heterotic orbifold models describable by our SU6 orbifold gut. Thank you.
Yeah, just for clarification, how many supersymmetries do we have in 6 dimensions? Is it 8 or 16 supercharges?
2. N equal 2 in 6 dimensions.
Yeah, so n equal 2, so it's 8 supercharges. And,
and effectively in 4 dimensions is n equal to 4.
16. And it's 16.
In 6D would be, if you had n equal to 1 in 6D, in 4D it would be n equal to 2. And if it's n equal to 2 in 6D and 4D, it's n equal to 4.
Yes.
So, I have a very basic confusion. So, how would you define the spinors on the projective plane?
There is no problem with putting spinors on the projective plane, and you're asking me, it's not it's
a global obstruction because.
In fact, it's a good question, and we asked this question ourselves, but then we looked at the book by Green, Schwartz, and Witten, and in the back they describe the fact that you can put fermions on the real projective plane. There's no problem.
Is that related to your observation that you need n equals to 2 and not n equals to 1 in 16?
Well, is that related? It may or may not be. I don't know. I mean, it's very simple to see that you can't, if you try to do this, well, the x5 goes to minus x5 plus a shift, and x6 goes to x6 plus a shift is equivalent to z goes to z star. So it's not holomorphic. And if you try to do that on your field theory, you don't have a symmetry, so you just can't do it. But I don't know how to see that in terms of the manifold for fermions.
Okay, well I see no further questions, so let's thank Stuart again.